This is Unit 2G that deals with space and the solar system in particular. So moving left to right here, we have not at all to scale the Sun, and around the Sun we have some comets. Now the planets orbit in roughly circular orbits. They're slightly squashed, they're ellipses, but comets have very obviously elliptical orbits. So the period of a comet is the time it takes to go around the Sun. It can vary enormously from hundreds of thousands of years to tens of years. Now the thing that we know most about, or comets are known for, are their tails. They don't always have their tails, they only have them when they're near the Sun, because it's the blast of the solar wind and the heat, the energy that creates the tails, and they always move away from the Sun irrespective of their motion. It's a common misunderstanding. Often they have two tails. They have a gas tail and they have a dust tail. The comet is best described as a dirty snowball, so it contains ice and rock and so on, and as we said, when they come close enough they will melt and they'll stream away. Many tens of thousands of kilometers long the tails can be occasionally, and they're also lit up by the Sun, which is why we can see them from Earth. So moving out to Earth itself then, let's have a think about two things here: meteors and meteorites. Now both of them can come from space, or they both do come from space. The asteroid belt is a belt of small rocks, or rocks of varying sizes between Mars and Jupiter. They can come from further afield, but a lot of them come from the asteroid belt, and they get knocked out of this belt for various different reasons. Now if the rock or the asteroid burns up in the atmosphere, we call it a meteor. It's sometimes called a shooting star, although it's got nothing to do with stars at all. If it reaches the surface, as we can see here, then it's called a meteorite. Now many of them are very small and harmless, but they can be enormous. So this is one example from about 50,000 years ago, the Barringer crater in Arizona. It's about a mile across, and a very, very impressive impact it is indeed. Now erosion hasn't had a chance to clean this up yet, but it has done it with the Yucatan Peninsula crater in Mexico, and this was only recently discovered, but we can see deep down traces through gravity imaging of the crater. Now this is a crater that's much bigger than the Barringer one, tens of kilometers across, more than 100 kilometers across, and it's quite likely that this impact is what killed the dinosaurs. So let's have a look at exploration. So this is the Moon, again not to scale, which is really as far as we humans have gone. Now the advantages of human exploration are the sense of adventure, the fact that we can adjust equipment and make running repairs and so on, but it is incredibly expensive, and it is also very, very dangerous for the astronauts involved. Now we can contrast that with robotic or unmanned exploration and flight, which is totally safe in the sense that no humans can die. It's relatively cheap, and we emphasize the word relatively, and robots can go to very, very harsh places where we would never dare go. Venus is a good example of this. There are no plans to send humans there. But they are relatively inflexible, and they need to be incredibly reliable. If some tiny thing goes wrong, they really can't repair themselves. Now let's have a think about orbits more generally. We've seen in the previous slide that we've got these elliptical orbits, but what causes them? Well, objects have a natural tendency to want to carry on in a straight line. If we give something a push, it will carry on in a straight line unless there's a force, and the force that is provided in this case is from the Sun, and we call this centripetal force, which is constantly turning the planets from their straight direction, and a turn eventually becomes an orbit. Let's look a little bit more detail at some of the history behind this, particularly our view of ourselves. So let's start over here with a commonsensical view of the solar system, or the whole universe, or the cosmos, as our ancestors would have called it. So here we've got the Earth at the center, and this makes perfect sense because it's not obvious that the Earth is moving at all, and the planets and the Sun going around. And this also fits with religious ideas that the Earth is created for man, so of course it's at the centre of things. Now Galileo, amongst others, Copernicus, began to challenge this view, and the idea had been around for a while, but Galileo actually had some evidence, and mainly because he had a telescope. One of the pieces of evidence was retrograde motion. Now what this is the undertaking of the Earth of Mars and other planets. So normally Mars moves in our sky a little bit every night, as we would expect. But as I said, because the Earth is orbiting more quickly, we actually get certain moments when it moves in the opposite direction. And there's no way of explaining this if the Earth is at the centre of things. Galileo also saw Jupiter's moons in his telescope, which is like a mini solar system. So if we have something orbiting around something other than the Earth, very obviously this again began to challenge the idea of the Earth being at the centre of things. In the 20th century we discovered other things about our expanding universe. So here we've got Big Bang, and we've got various stages after the Big Bang, and all these galaxies are moving away. Well, how do we know they're moving away? It's because of something called redshift. So as the universe is stretched, the light that's sent in all directions is being stretched. So it may start off as blue, but it ends up as red. We haven't got anything quite that extreme on this illustration, but we can see that it moves. So let's imagine we've got two galaxies here, both of which send off green light. So they both are genuinely sending green light. But this one at the bottom is further away, and it's moving faster. So there's more expansion happening in the space between us and it. So by the time it arrives, it's stretched to red. Whereas this one is also going to be stretched, but not as much, so only to yellow. Now, how do we know it wasn't yellow to begin with? That's the obvious question, or red to begin with. Well, we know because of these dark bands here, a bit like a barcode, and they relate to particular gases and elements, and we know where these dark lines are supposed to be, or where they are if the object we're looking at is very close to us. So we can see that in these red-shifted sources of light, they're not where they're supposed to be, so we can work out how far away and how fast something is moving.